Welcome to this topic on retrofitting principles for climate and risk. In today's lecture, we will explore how existing urban environments can be strengthened to cope with the growing pressures of climate change and natural hazards. Retrofitting plays a central role in helping cities remain safe, functional, and equitable in the face of rising temperatures, extreme rainfall, aging infrastructure, and diverse environmental risks. Rather than focusing only on new construction, this topic emphasizes the value of improving what is already in place. Throughout this session, we will build a foundational understanding of what retrofitting means, why it matters, and how it can be applied across different urban scales in a practical and forward-looking way. In this session, we will achieve several core learning objectives. We will begin by defining retrofitting within the context of climate adaptation and risk reduction. Then we will examine the main principles and approaches used to upgrade the existing urban fabric in a resilient way. We will also look at the primary categories of technical, spatial, and policy-related strategies that shape climate-resilient retrofitting in practice. A significant part of this lecture focuses on hazard, exposure, and vulnerability dynamics, because these concepts help explain how risk is produced and where retrofit interventions are needed most. Finally, we will highlight why equity and multi-scalar thinking are essential for informed adaptation planning and for making retrofit actions more effective over time. Retrofitting refers to upgrading existing buildings, infrastructure, and public spaces so that they can better withstand climate and hazard-related stresses. Rather than rebuilding from scratch, retrofitting strengthens what already exists and improves performance under changing environmental conditions. This may include improving thermal comfort, protecting against flooding, addressing seismic vulnerabilities, and enhancing energy efficiency. Importantly, retrofitting can occur across multiple scales, from individual buildings to streets, neighborhoods, and entire districts. It also helps avoid the major disruption associated with demolition and full redevelopment. For example, adding shading devices and natural ventilation systems is often far more practical than tearing down and reconstructing a whole structure. In this sense, retrofitting is both a physical and strategic response to climate risk. Cities today face climate conditions that many of their existing buildings and infrastructures were never designed to handle. Heat waves are becoming more frequent, extreme rainfall is more intense, and infrastructure systems are aging faster than they can be fully replaced. Under these pressures, waiting for complete redevelopment is often unrealistic. Retrofitting provides a pragmatic, relatively fast, and cost-effective adaptation pathway. It allows cities to reduce climate risk without large-scale demolition, displacement, or the heavy financial and ecological burdens of starting over. In dense urban areas, especially where vulnerable populations are concentrated, retrofitting helps maintain social continuity while improving safety, comfort, and resilience. For many cities, it is one of the most realistic ways to adapt existing urban environments to future climate conditions. Resilient retrofitting focuses on four main targets, each closely linked to a key climate hazard. The first is thermal comfort, where shading, insulation, and natural ventilation help reduce excessive heat and improve indoor conditions. The second is flood protection, which involves interventions such as permeable surfaces, improved drainage, and water storage or retention areas. The third target is seismic safety, where structurally vulnerable buildings may require reinforcement to reduce potential damage and human risk. The fourth is energy performance, where better building envelopes and more efficient systems reduce emissions while also improving comfort. These targets are interconnected, but each city will emphasize them differently depending on its hazard profile, climate conditions, and the characteristics of its existing built environment. Retrofitting is more than a technical repair, it is a strategic form of climate adaptation. By upgrading the existing urban system, retrofit actions can reduce both exposure and sensitivity to hazards, particularly in areas that are already under pressure. In this way, retrofitting helps cities respond to present climate risks while preparing for future uncertainty. It also supports flexible and incremental adaptation pathways, meaning that improvements can be implemented in stages as new climate information, funding opportunities, or policy priorities emerge. Beyond direct risk reduction, well-designed retrofits can also deliver important environmental, social, and economic co-benefits. These may include better public health, improved comfort, reduced energy consumption, and a stronger overall capacity to cope with climate stress over time. Different cities face different combinations of climate hazards, and resilient retrofitting must respond to these local conditions. Some cities struggle primarily with extreme heat and urban heat island effects, while others face pluvial flooding caused by intense rainfall, fluvial flooding associated with rivers, or coastal flooding linked to storm surge. In many places, storms and wind hazards are also increasing, and in some regions seismic risk remains a major concern alongside climate-related threats. Importantly, cities are often exposed to more than one hazard at the same time. This creates compound or cascading events, such as a storm that overwhelms drainage systems and increases flood damage across a wider area. Understanding which hazards are most critical in a specific context is the first step toward planning effective retrofit measures. Risk is shaped not only by the hazard itself, but also by who and what is exposed, and by how vulnerable they are. Exposure refers to the people, buildings, infrastructure, and assets located in hazard-prone areas. Vulnerability, in contrast, combines sensitivity with adaptive capacity. In other words, it reflects how strongly a population may be affected and how well it can cope with impacts. Elderly residents, low-income households, and communities with limited access to cooling, drainage, healthcare, or safe buildings are often more at risk than others. This means that two areas exposed to the same hazard may experience very different outcomes. Retrofitting should therefore prioritize places where high exposure and high vulnerability overlap, because these locations often face the greatest need and the greatest potential benefit from intervention. To plan effective retrofits, cities must move from intuition to evidence, and multi-hazard assessment is one of the most useful ways to do this. By combining hazard maps, exposure data, and vulnerability layers, usually within a GIS environment, planners can identify the locations where overall risk is highest. These priority zones are where retrofit interventions can produce the greatest benefit. This type of assessment supports more targeted and transparent decision-making, especially when resources are limited and not every area can be upgraded at once. It also helps cities compare different risk factors within the same spatial framework. As a result, retrofit planning becomes more strategic, more place-sensitive, and better aligned with actual conditions on the ground, rather than relying only on assumptions or isolated observations. Adaptation pathways allow cities to sequence retrofit measures over time instead of treating adaptation as a single one-time action. This is important because climate conditions are changing, and social as well as economic contexts evolve as well. Decisions made today should therefore improve current conditions without limiting future options. By prioritizing no-regret and low-regret measures, such as shading, insulation, permeable pavements, or drainage improvements, cities can implement practical interventions now while keeping room for more substantial upgrades later. This phased approach promotes flexibility and helps decision-makers respond as knowledge improves or risks intensify. It also helps avoid maladaptation, meaning solutions that may work in the short term but become ineffective, costly, or even harmful under future climate conditions. To guide the design and implementation of effective retrofits, we use 5 core principles. These principles help ensure that interventions strengthen resilience while preserving the social and spatial continuity of urban life. They are relevant across all scales, from a single building to an entire district. The first principle is to minimize disruption. The second is to maximize adaptability. The third is to use low-carbon and nature-based solutions. The fourth is to ensure climate justice and social equity. The fifth is to integrate actions across multiple scales. Together, these principles provide a clear framework for evaluating retrofit choices and for shaping interventions that are not only technically effective, but also socially responsible and environmentally sustainable. The first principle is to minimize disruption. Retrofitting should enhance resilience without causing unnecessary harm, displacement, or loss of everyday urban function. This means working with the existing urban fabric rather than replacing it whenever possible, and prioritizing non-invasive, reversible, or incremental interventions that can be implemented with limited interruption. Minimizing disruption is especially important in dense neighborhoods, active public spaces, and communities where social networks are essential for daily life and recovery. If retrofit actions create major instability, they may undermine the very resilience they aim to support. A careful retrofit approach therefore seeks to improve performance while allowing residents, services, and local activities to continue as smoothly as possible throughout the process. The second principle is to maximize adaptability. Because future climate conditions remain uncertain, retrofit design should avoid rigid, one-time solutions that are difficult to adjust later. Instead, it should support modular, scalable, and flexible systems that can be expanded, modified, or combined with future interventions. Adaptive retrofits allow buildings and public spaces to evolve as climate risks, technologies, and policy frameworks change over time. This reduces long-term costs and helps maintain functionality under uncertain conditions. In practice, maximizing adaptability means leaving room for future upgrades and choosing solutions that do not close off better options later. In this way, retrofitting becomes an ongoing process of learning and adjustment rather than a fixed final answer to climate risk. The third principle is to use low-carbon and nature-based solutions. Nature-based solutions are among the most powerful tools available for climate resilience because they address environmental problems while also improving urban quality. Green roofs, bioswales, permeable surfaces, shaded planting, and restored vegetation can help manage water, cool urban environments, and support biodiversity at the same time. These strategies often rely on low-carbon materials and processes, allowing cities to address mitigation and adaptation goals together rather than treating them separately. They also tend to generate multiple co-benefits, such as improved public space, better air quality, and enhanced ecological performance. For these reasons, nature-based and low-carbon strategies are essential components of sustainable retrofitting in a changing climate. The fourth principle is climate justice and social equity. Climate hazards do not affect all communities equally, and retrofit planning must recognize this uneven reality. Low-income and marginalized populations are often more exposed to risk and have fewer resources for preparation, recovery, or self-protection. As a result, retrofitting should prioritize vulnerable groups and ensure fair access to cooling, drainage, safe infrastructure, and other protective measures. It is also important to avoid maladaptive outcomes, such as projects that improve one area while unintentionally deepening inequalities elsewhere. Climate-just retrofitting requires attention not only to technical performance, but also to who benefits, who is protected, and whether interventions support long-term well-being and social inclusion. Equity is therefore not an optional addition but a central condition of resilient adaptation. The fifth principle is multi-scalar integration. Urban climate risks operate across multiple scales, so retrofit actions must also work across multiple scales in a coordinated way. Building-level upgrades should not be planned in isolation, they need to align with street-level infrastructure, neighborhood systems, and wider city strategies. For example, a building may improve its own thermal performance, but broader resilience also depends on public shade, drainage networks, open space systems, and district-wide planning decisions. Integrated multi-scalar approaches prevent fragmented efforts and help ensure that local interventions contribute meaningfully to larger resilience goals. Without this coordination, retrofit projects may remain isolated and less effective. Multi-scalar thinking therefore helps connect individual measures into a broader, more coherent adaptation strategy. We now turn to the main categories of retrofit strategies. These include building envelope upgrades, greening initiatives on rooftops and in public spaces, floodproofing measures, and smart or modular interventions. Each of these categories responds to different but often overlapping climate risks, including heat stress, flood exposure, and energy challenges. They can be used separately, but they are often most effective when combined as part of an integrated retrofit package. The following slides expand on each of these categories in more detail. Together, they illustrate how resilient retrofitting moves from general principles into specific forms of intervention that can be adapted to local conditions and applied across a range of urban contexts. Envelope upgrades improve both thermal comfort and energy efficiency, making them one of the most common retrofit strategies. This includes insulating walls and roofs, installing high-performance glazing, using shading devices, and applying reflective or cool roofing materials. Such measures can significantly reduce indoor heat stress, lower energy demand, and improve comfort during extreme weather events. They are especially important in places where existing buildings trap heat, lose energy, or provide weak environmental protection. In addition to immediate comfort benefits, envelope improvements also support longer-term climate adaptation by making buildings more stable and efficient under changing conditions. As a result, they represent a practical way to strengthen building performance without requiring complete reconstruction. Greening interventions are central to resilient retrofitting because they address several urban climate challenges at once. Green roofs and walls help cool buildings naturally, increase stormwater retention, and support biodiversity within dense urban environments. Street trees, shaded sidewalks, and greener public spaces create more comfortable microclimates and reduce direct heat exposure for residents. At the same time, permeable surfaces and ventilation corridors can improve water infiltration and airflow, which helps cities manage both heat and rainfall more effectively. These measures also contribute to livability by making urban environments more pleasant and usable. When applied strategically, greening interventions strengthen environmental performance while also supporting public health, outdoor comfort, and broader climate resilience. Effective floodproofing combines structural and nature-based measures to reduce water-related risk. Upgrading drainage systems through bioswales, permeable pavements, retention areas, or modernized infrastructure help cities manage intense rainfall more effectively. Flood barriers and raised thresholds can prevent water intrusion into buildings, while elevating critical infrastructure reduces the likelihood of major damage during flood events. Retention and detention zones also help slow and store runoff, which reduces pressure on drainage systems and protects surrounding assets. These measures can be relevant for pluvial flooding, fluvial flooding, and in some contexts coastal flooding as well. By reducing both direct damage and system overload, floodproofing interventions play a critical role in climate-resilient retrofitting. Smart and modular interventions support adaptive resilience by helping retrofit systems respond over time. Sensors that monitor heat, humidity, and water levels provide real-time data that can inform maintenance, warning systems, and day-to-day decision-making. Energy monitoring tools improve efficiency and help users better understand how buildings perform under different conditions. Modular, plug-in retrofit elements also make it possible to upgrade spaces without major disruption, which supports flexibility and phased implementation. In addition, early warning technologies can reduce harm during extreme events by improving preparedness and response. Together, smart and modular systems allow cities to learn from changing conditions and adapt continuously, making retrofit actions more responsive, manageable, and future-oriented. To conclude, retrofitting is one of the most effective and essential pathways for building climate-resilient, sustainable, and equitable cities. It strengthens existing systems without major disruption and, when done well, delivers multiple co-benefits, including improved health, greater comfort, lower energy use, and long-term cost savings. Successful retrofitting requires integrated, multi-scalar, and context-specific strategies that respond to local hazard conditions while also supporting broader urban resilience goals. It also requires attention to justice, adaptability, and environmental responsibility. Most importantly, retrofitting should be understood not as a one-time upgrade, but as a long-term adaptation pathway that evolves together with changing climate conditions, urban needs, and emerging knowledge.